Welcome to The Explainer. Today, we're cracking open a scientific case file, a real mystery that started with just an accidental spark and ended up changing physics forever. Okay, let's dive right in. We're going to head back to the late 19th century and follow the trail of evidence. Now, our lead investigators are Hertz, Hallwachs, and Lenard. These are the folks who, along with a huge discovery by J.J. Thomson, pieced together a puzzle that, honestly, nobody even knew was there. You know, every great mystery seems to start with a single, unexplainable event. And for this case, it all began back in 1887 with a physicist named Heinrich Hertz. Now, Hertz wasn't even looking for this. He was deep in his work on electromagnetic waves, and he just happened to notice something odd. The sparks jumping across his equipment were, well, brighter, and they jumped more easily whenever they were hit by ultraviolet light. You can see it here. In the dark, you get a standard spark. But shine some UV light on it, bam, an enhanced discharge. This was our very first clue. Light was somehow helping electricity flow. A clue is one thing, right? But to really build a case, you need hard evidence. So let's move into the lab and see how the investigation starts to heat up. So enter investigator Philip Lenard. He takes this whole situation from the open air into a much more controlled environment. He built this special glass tube and pumped all the air out to get rid of any other variables. The setup was actually pretty straightforward. A UV light source shines through a quartz window and hits plate C, which we call the emitter. Then, across from it, you've got plate A, the collector. The question was simple. What actually happens when that UV light hits the emitter plate? And the result? Well, this chart lays it out perfectly. It was like flipping a switch. When the UV light was on, the little meter, the galvanometer, it detected an electrical current. As soon as the light was turned off, nothing. The circuit was totally broken. Lenard's deduction was sharp. The light itself was making the current flow. It had to be knocking some kind of particle off the emitter plate, which then zipped over to the collector and completed the circuit. At the same time, another investigator, Wilhelm Hallwachs, was running his own experiments in 1888. He took a zinc plate and zapped it with UV light under 3 different conditions. First, when the plate was already negatively charged, it lost its charge. Interesting. Then, when it was uncharged, it actually became positive. And when it was already positive, it just got even more positive. The verdict was crystal clear. The light was specifically kicking out negatively charged particles. So the evidence was really starting to mount. Our investigators knew something was being emitted, and they knew its charge was negative. Now, they just needed to put a name to the face to identify the culprit. And then, in 1897, the final piece of the puzzle just clicked into place. Thanks to J.J. Thomson's discovery of the electron, that was it. That was our negatively charged particle. The case of the mysterious spark was officially closed. The incident light was liberating electrons from the metal. And with the culprit identified, the phenomenon finally got its official name, the photoelectric effect. It makes perfect sense, right? Photo for light and electric for, well, the electrons. And the little electrons themselves that get kicked out, we call them photoelectrons because they're born from light. So we know what happens. Case closed, right? Well, not exactly. For any good investigator, the next question is always, how? What's the modus operandi here? What's the actual mechanism behind this crime of electron emission? Okay, let's zoom way in, down to the microscopic level. A metal surface is just teeming with these free electrons, but they're basically trapped by the attractive forces of the positive ions in the metal. The incoming light radiation delivers these little packets of energy directly to the electrons. And if an electron absorbs just enough energy to overcome that attractive force holding it back, poof, it escapes and becomes a photoelectron. But this is where things get really weird. It led to a whole new puzzle. The investigators noticed that just blasting the metal with more light, making it brighter, didn't always work. The type of light was what really mattered. Now this slide right here is the part that just blew everyone's mind. It completely defies intuition. Look at scenario A. You can hit a metal with a super bright, intense red light, which has a low frequency, all day long, and absolutely nothing happens. No electrons pop off. But then look at scenario B. Even a really faint UV light, which has a high frequency, can immediately kick an electron out. So it's not about the intensity, it's all about the frequency. And this all boils down to a super important concept called threshold frequency. Basically, every material has this minimum frequency, a specific energy level it needs to be hit with before it'll let go of any photoelectrons. It's kind of like a key needing to be the right shape for a lock. It doesn't matter how many wrong keys you try or how hard you jiggle them, that door is not going to open. And that threshold is different for every material. You've got these stubborn materials like zinc and cadmium that have a really high threshold. They only respond to high-frequency ultraviolet light. But then you have this more sensitive group, the alkali metals like sodium and cesium. They're way less picky and will start emitting electrons even when they're hit with lower-frequency visible light. So the case was solved, but the fallout, the implications, they were way bigger than anyone could have possibly imagined at the time. This wasn't just some weird little quirk of lights. It was the key that unlocked a whole new reality. So let's do a quick rundown of the complete case file. We have a source of energy, the incoming light. We have a liberated particle, the electron. There's a mechanism of escape. The energy it absorbs has to overcome the attraction. And we have that crucial constraint. The light's frequency has to be higher than the material's threshold. And here it is, the earth-shattering takeaway, the twist ending that changed everything. These experiments proved that light doesn't just act like a wave, which is what everybody had thought for a long, long time. It also acts like a stream of tiny, discrete packets of energy, like particles. We later named these photons. This is the dual nature of radiation. This discovery of light's dual nature became the experimental bedrock for a whole new kind of physics. It completely shattered the old classical ideas and threw open the door to the strange, wonderful, and mind-bending world of quantum mechanics, a world we're still exploring today. It all just started with a simple little spark. And it really makes you wonder, doesn't it? If a beam of light was hiding a secret this big, what other quantum mysteries are out there, waiting to be solved, maybe right in front of our eyes? Thanks for joining this explainer.